Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to Madam Farah Yasmin, my lecturer for ECE521. This is my lab report of Lab 1, ARM Assembly Language, Programming Data Transfer, Data Processing, and Addressing Modes. So the objective for this lab, number 1, students are able to write simply assembly language programs for the ARM microcontroller using data transfer, data processing instruction, and addressing mode. Number 2, students are able to execute the program using an ARM skill editor or assembler or simulator. Moving on to our procedure of this lab. For exercise number 1, write a program that will store 0x30 into R0, copy the content of R0 into R5, and then save data 0x45785612 into memory location 0x40000030. Execute the program and explain the differences in the results. Also discuss the addressing modes of each instruction used. And hence, this is the programming code of my exercise number 1. So the code for line 5 is MOV R0 hashtag 0x30. So we know that move value of 0x30 into register 0. We can see in register 0, we have the value of 0x00000030. Next, MOV R5 R0. So the value of R0 will move into R5. And hence we have the same value of R5 and R0, which is 0x00000030. Next is LDR R0 with equal to 0x45785612. Hence we look at our register R0, we have the value of 0x45785612. Next, LDR R5 0x40000030 when we have the value of 0x40000030 in R5. Next is SDR R0 in R5. So we will look at our memory address of R5, which is 0x40030. It will contain the value of what's in register R0, which is 45785612. So the differences between these two results is in the upper part of the coding, the changes made is only on the register part, while there is no changes on the address memory part. And the letter coding, starting from LDR to SDR, it changed the addresses of 400030 that contain the value of R0. The addressing mode used for each instruction for line 5, immediate addressing, line 6, register addressing, line 7, immediate addressing, line 8 is also immediate addressing, and lastly line 9 is register indirect post-index offset. Moving on to exercise 2, write and execute a program that will add 0x20 FE5690, 0x FE123089, and 0x34589710, and save the sum in register R7 record the changes in CPSR as well. So by executing, in line 4, we have LDR R1 equal to 0x20FE5690. Now we have in our register R1 a value of 0x20FE5690. Next, LDR R2 0xFE123089. So in our register 2, now we have the value of 0xFE123089. Next, LDR R3 0x34589710. And now in register R3, we have the value of 0x345890. Before we proceed with the next line, we have to look in our CPSR. The value of N is 0, Z is 0, C is 0, and B is also 0. Executing the next line, ADDS R4, R2, R1, we know that by this instruction ADDS, our CPSR will change, and we know that this operation is R2 plus R1 and is saved in R4. And now in our register, we can see that in R4, we have the value of 0x1F108719, which is the addition of R2 and R1. And also in our CPSR, we are now having a C flag of 1. Next is ADDS R7, R4, R3. And again, this instruction also will change our CPSR. And the operation, we know that R4 plus R3 and is stored in R7. So now we have in register 7 a value of 0x53691E29, and our CPSR, which is our C flag just now, was 1, and after executing the line, now we have our C is equal to 0. Moving on to exercise 3, write a program that will store 0x2936FEDA in R8 and then perform the following instruction on the content of the register 4 times. Comment on your result. Roman 1 ESR, Roman 2 LSL, and Roman 3 ROR. Executing the code. Line 4, we have LDR R8 equal to 0x2936FEDA. So in our register R8, we have the value of 0x2936FEDA. Next, MOV R1 hashtag 4. So in register R1, we have a value of 0x00000004. Next is ESR R9, R8, R1. Now we have arithmetic shift right operation, and after executing the operation, we have in register 9 a value of 0x02936FED. Next, LSL R9, R8, R1. This operation is logical shift left, and after executing this operation, we have in R9 value of 0x936FEDA0. Next, ROR R9, R8, R1. This operation is rotate right, and after executing this operation, we now have in register 9 value of 0x8936FED. Next, exercise 4. Write a program that will perform logical OR 0x6398 with 0x1DFE. Execute the program and comment on the result. Here we have our coding. On line 4, we have move MOVW R0 hashtag 0x6398. And now we have in R0 a value of 0x00006398. Next, MOVW R1 hashtag 0x1DFE. And now in register R1, we have value of 0x000001DFE. Next, ORR, R2, R1, and R0. We know that this operation will perform a logical OR on R1 and R0, and the result it will be saved on R2. Now we can see in register R2, we have a value of 0x00007FFE. Next, exercise 5. Write a program that copies 12 bytes of data starting from memory location 0x40040000H to memory location starting 0x40040020H. Set manually the content of memory in 0x40040000H until 0x40040000BH to be 0x01, 0x02, and so on. Run on the program and comment on the result. Hence, here is my coding, and I have set manually the content of memory 0x40040000 to be 01 until 0x40040000B we want to. Executing line number 4, we have LDR R0 equals to 0x40040000. So in register R0, we have 0x40040000. Next, LDR R1 0x40040020. So in register R1, we have value 0x40040020. Next, MOV R2 hashtag 3. So in R2 register, we have a value of 0x00000003. Next, LDR R3 bracket R0 hashtag 4. So for this line, we know that R0 content of memory of R0 will be stored in R3, and then the memory address for R0 will increase by 4. So hence, when we look at our register, we see that R3 has a value of 0x04030201, which is the content of memory here, and then R0 now is 0x40040004. Next, STR R3 R1 bracket R1 hashtag 4. So for this one, we know that the whatever value in R3 will be stored in the content of memory of R1, and then the memory address of R1 will increase by 4. So we see at our register 1, our value has increased to 0x40040024. And here we can see on the memory address of 0x40040020, we have the value of 01 until 04. Next, we have SUB R2 hashtag 1. So we know that this is the operation of subtraction. So R2 minus 1 and the result will be stored in R2. Hence, we have register R2 value of 0x 00000002. Next, we have CMP R2 hashtag 0. So this is the operation of compare R2 with 0, which the operation will execute as R2 minus with 0. And this also will change the CPSR flag. So here we can see that C is now equals to has a value of 1. Next, we have B and E ulang. So for this branch is actually a branch not equal when which the conditions are Z equals to 0. When Z is equals to 0, this ulang loop will rerun again until the Z is not equal to 0 anymore. And here we can see Z is still equals to 0. Therefore, we still rerun this line up to line 11. Again, after executing that line, we have LDR again with R3 bracket R0 hashtag 4. But now we have a value of R0 increases to 0x 40040008, and the value in R3 is 0x 08 07 06 05. Next, we have STR3 bracket R1 hashtag 4. So we have the value of R1 increases by 0x 40040028, and then in the content of memory, we have now 04, 05, 06, 07, and 08. Next, SUV R2 hashtag 1. Again, R2 has the new value of x 0x00000001. Next, we have CMP R2 hashtag 0. So compare again the value of R2 with 0. Next, we have B and E ulang. Since Z is still equals to 0, so this branch will loop again to ulang. Next, we have LDR still R3, R0 hashtag 4. And now we have register R0, a value of 0x 40040000C. And the value of R3 is 0x 121110 and 09. Next, STR R3 R1 bracket R1 hashtag 4. We have value of 0x 40040002C in register 1, and in the memory address as well, we have already stored 09, 1011 and 12. Next, SUB R2 hashtag 1. So again, R2 will subtract by 1, and now we have a value of 0x00000000 in R2. Next, compare CMP R2 hashtag 0. Since now we are comparing 0 minus 0, therefore our CPSR flag has changed, which our Z flag has become 1. Next, B and E ulang. So the condition for B and E to loop again at ulang, the C must be equal to, the Z must be equal to 0. But now our Z is equal to 1. Therefore, it will execute the next line, which is line 12. Next, exercise number 6. Write a program to compare data in num into register R2. If the data is greater than 5, store the data in memory location 0x40020000. Otherwise, add the data with 0x60 and store it in memory location 0x40020010. Before that, set the number with value 3, use EQU instruction, run the program and comment on the result. Hence, we have our coding here. Line number 4, MOV R1 hashtag num. So we have in our register R1 a value of 0x00000003. Next, MOV R2 hashtag 5. So we have in R2 value of 0x00000005. Next, LDR R3 equals to 0x40020000. So in R3, we have value 0x40020000. Next, LDR R4 equal to 0x40020010. So we have in register R4 value of 0x40020010. Next, we have CMP R1 R2. So this will compare the value of R1 and R2, which the operation is actually R1 minus R2. We can see from that execution of program coding, we have our CPSR changing value of n equals to 1. And then next, we have BLO small. So this is branch lower. So the condition is when C is equal to 0, the branch will go into small loop. Hence, by executing the CMP, the previous code, we have C is equal to 0. Therefore, we are moving forward to line number 12. So, in line number 12, we have ADD R5 R1 hashtag 0x60. So, we know that this is the operation of addition. R1 plus 0x60 and it is stored in R5. So, in register R5, we have the value of 0x00000063. Next, we have STRB R5 bracket R4. So we know that this is to store the value of R5 into the content of memory of R4. So whatever in R5 will be stored in content of memory of R4. So now we have in the content of memory of R4, which is 0x40020010, we have the value of 63. Next, branch to habis, and then we also have the initial set of num equals to 3. That is all on the exercise part. In conclusion, these labs are executed smoothly and successfully by ARM-Kill editor, assembler, or simulator. Data transfer, data processing instruction, and addressing modes of ARM microcontroller assembly language are learned and used in writing the coding of this lab. Therefore, all the objectives stated in this lab has been achieved successfully. Thank you.